If you go back just a decade, this material barely existed outside a handful of experimental labs on the East Coast. But today, if you walk through a growing number of green certified buildings across the United States, you can find walls made from bricks that were never touched by fire. They're called BioMason bricks, and they have been documented by independent testing to match the compressive strength of fired clay brick, while producing roughly 90% less carbon emissions, using nothing but sand, bacteria, and a few days of room temperature growth. But if this material is really that effective, why isn't it replacing every kiln-fired brick on construction sites right now? And if it can actually be grown instead of baked, should we be building with it already? Let's find out. The idea of using biology to solidify loose material into a solid structural mass is one of the newest engineering solutions in human history. We've already covered a version of this mechanism. Ancient builders used to work with mineral cementation this way, observing how natural limestone forms slowly from compressed sediment over millennia. But nature had never needed a laboratory to speed that process up to just a few days before. In the research labs of North Carolina State University, a materials scientist faced a problem no traditional manufacturing method could solve. The kiln firing process used to make a standard clay brick requires heating raw material to temperatures exceeding 1,800 Fahrenheit, and doing that at the scale of the global construction industry accounts for a significant share of total industrial carbon emissions. Improving insulation on the kilns themselves could reduce fuel use marginally, but it did nothing to eliminate the fundamental need for combustion in the first place. Concrete block was an alternative, but manufacturing cement releases its own substantial carbon footprint through the calcination of limestone. So in 2007, a scientist named Ginger Krieg Dossier turned to a process already found in nature, microbially induced calcite precipitation, and applied it to a mechanical mold instead of a seashell. And unlike anything built from fired or poured material, this brick forms itself directly out of loose sand held together by mineral crystals grown by living bacteria, requiring no kiln, no cement, and no combustion of any kind. Dossier's technique is simple, yet extraordinarily elegant, drawing on three separate biological principles that work together to fix a problem no purely mechanical process can solve on its own. Ordinary sand is packed into a brick-shaped mold and inoculated with a naturally occurring bacterium, typically Sporosina pasteurii, mixed into a nutrient-rich solution containing calcium and urea. Once the bacteria begin metabolizing the solution, they trigger a chemical reaction, the same way a seashell gradually forms its own hardened structure from dissolved minerals in seawater. The first principle at work is enzymatic hydrolysis. As the bacteria break down urea in the solution, the reaction raises the local pH around each grain of sand, creating the exact chemical conditions needed for dissolved calcium to bond with carbonate ions and precipitate as solid calcite crystal. The key point here is that unlike a fired brick, which achieves hardness through the destructive melting and fusing of clay particles, this brick achieves hardness through additive mineral growth, meaning individual sand grains are being cemented together rather than transformed by heat. But here's what most people don't realize. The brick doesn't stop hardening once the initial crystals appear. You see, it also leverages something called progressive pore-filling, where newly formed calcite crystals continue bonding into the microscopic gaps between sand grains over several growth cycles. thickening the mineral matrix and adding structural density exactly where the loose material would otherwise remain weak. In a brick left to grow for the full cycle, this ongoing crystallization creates a dense, interlocked lattice that reaches full strength without ever touching an open flame. The third principle is load-responsive densification. As the bacterial solution is reapplied in repeated cycles, each layer of crystal growth compounds onto the layer beneath it, a process closely monitored to ensure uniform strength throughout the brick rather than just at the surface. All three of these effects compound one another. The result is a material that achieves comparable structural performance to a kiln-fired brick while consuming a fraction of the embodied energy. And this simple technology has been proven to be remarkably effective. Independent structural testing conducted on BioMason's commercial product line found that the finished bricks meet ASTM compressive strength standards required for load-bearing masonry construction, performing comparably to standard fired clay brick in side-by-side testing. And field data from the company's manufacturing facility showed that eliminating the kiln firing step reduced the carbon footprint of each individual brick by approximately 90% compared to a conventionally fired equivalent. To put that in practical terms, a standard fired brick requires several days inside a kiln burning at temperatures exceeding 1,800 Fahrenheit, consuming a substantial quantity of fossil fuel per batch. BioMason's process instead requires several days at ambient room temperature, consuming no combustion fuel of any kind, only the modest electricity needed to circulate the nutrient solution through the growing chamber. But these numbers come with an important caveat, and it's part of the reason why grown bricks have become far less common than the results alone would suggest. A study reviewing early-stage biocement manufacturing found that scaling bacterial brick production to match the output volume of a conventional kiln facility requires significantly more floor space and time per batch, since the mineral growth process cannot be accelerated the way a firing cycle can simply by increasing kiln temperature. Their conclusion was that current production facilities remain limited to specialized smaller-scale manufacturing runs rather than the massive continuous output a traditional brickyard delivers. And this is where production capacity becomes critical. A single conventional kiln can output tens of thousands of bricks per firing cycle, while a bacterial growth facility of comparable size produces a small fraction of that volume in the same time frame. But the production capacity gap is only one piece of the story. The most problematic issue was material cost. The defining feature of this technology, its reliance on controlled bacterial cultures and nutrient solutions, is also the primary barrier keeping it from competing on price with conventional brick. Sourcing pharmaceutical-grade urea, maintaining sterile bacterial cultures, and running climate-controlled growth chambers all require specialized biological manufacturing knowledge. Expenses that most traditional masonry suppliers simply aren't equipped to absorb into their existing pricing structure. And there's a more subtle institutional problem, a kind of regulatory mismatch. This occurs when a building code committee prioritizes materials with decades of established performance data because they can be approved, insured, and specified within existing engineering standards. Because kiln-fired brick has over a century of accumulated failure data and testing precedent behind it, most commercial architects default toward the material with the deepest paper trail. For this reason, most structural engineers favor conventional brick and block. And because those materials are easier to specify without additional review, the BioMason technique is usually the one that gets left out of large commercial projects entirely. But beyond the specification gap, there is the issue of supply chain immaturity. Grown bricks depend on a small number of specialized manufacturing facilities, and in the construction materials industry, distributor networks drive adoption. Conventional brick, by comparison, can be sourced from thousands of established yards across the country with predictable lead times. General contractors across the country have frequently defaulted to conventional suppliers because they disrupt the standardized, dependable formula that makes large-scale project timelines financially viable. And even where environmentally focused developers have specified BioMason bricks for flagship green buildings, many nearby budget-conscious projects have worked around the higher unit cost by using conventional brick veneer paired with separate insulation systems, which produces a similar visual result but avoids the premium entirely. Insurance underwriting has also made it more difficult to implement BioMason at scale. As construction liability standards have become stricter around unconventional structural materials, insurers in many states now require extensive engineering documentation before approving any building specifying a newer masonry product. Because a BioMason brick's long-term durability data spans only a couple of decades compared to a century of fired brick performance, it falls into a cautious underwriting category in several markets. So, the real question we should be asking now is whether more construction should shift toward this material. And the honest answer depends entirely on what you're building and what you're trying to accomplish. If you're working on a project with strong sustainability goals or dedicated green building funding, LEED certified commercial developments, university research buildings, or similar environmentally driven projects, a BioMason brick specification remains one of the most effective ways to cut embodied carbon in your structure. The upfront cost per unit runs higher than conventional fired brick, while the environmental reporting benefit adds meaningful value for developers targeting sustainability certifications. For a project prioritizing a verifiable low-carbon footprint, the premium can be justified by the marketing and certification value alone. And because the finished brick contains no fired clay at all, the material can often be reclaimed and reprocessed at the end of a building's life far more easily than conventional masonry. But on projects without dedicated sustainability budgets or flexible timelines, a full BioMason specification is probably not a realistic choice. On tight-margin residential developments, the higher unit cost simply can't be absorbed without raising the overall project price, and a supply chain still limited to specialized facilities can't guarantee the volume or speed a large residential build requires. And in a market without established local distributors, the extended lead time would likely delay a conventional construction schedule beyond what most contractors can accept. In reality, for most immediate construction needs, particularly large volume ones, standard kiln-fired brick is probably the more practical choice. A conventional brickyard can deliver massive volumes within days rather than weeks, meeting an established code-certified specification without additional engineering review. And because it doesn't depend on specialized bacterial cultures, climate-controlled growth chambers, or a still maturing supply chain, it eliminates the production bottleneck that a BioMason system inherently carries. There are no fragile bacterial cultures to maintain, no unproven long-term data to defend to an underwriter, and no risk of a growth cycle failing to reach full strength. It just gets fired and it works exactly the way it always has. If you like this video and enjoy learning how modern science is quietly rebuilding the materials we've relied on for centuries, then subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. And if you want to see how scientists are growing entire coral reefs using nothing but electricity and seawater, then you need to watch our video on BioRock right here.